Um, okay, let me see if I can get this working here. Hopefully you all can see my screen and then we can get started. Well, first of all, I'm going to let you know, or kind of a disclaimer here. This was some data I collected while I was on sabbatical. And it was kind of one of the things. I went on sabbatical to Durham University a couple of years ago in the UK, right before COVID started. And Fulbright sponsored that, so I'm grateful to them for that. To mostly do stuff in Antarctica. But while I was over there in England, in the UK, I really wanted an opportunity to do some local field work. And so I had an opportunity to work with a couple scientists there at Durham University, Louise Best, Ian Shannon, David Small, and Sarah Bradley. And the way that this project started out is let's just go collect some data, some cores over on the coast of Northwest Scotland, since it's a particularly scenic area. And then as we kind of collected the data, we tried to think about what it all meant. And so hopefully I put together a story here that will make sense, but if it's a long and tortuous, sinuous curve to our final resting place, please forgive me for that. But hopefully at least you'll get some, as Jerry said, a few nice pictures of Scotland. So today, what I'm going to do, here's a nice picture of Scotland, right, on a snowy day as we were returning from the field. And I want to ask a question, and what role does relative sea level rise play in sort of the retreat of marine-based ice sheets and ice streams? And I'll take a few slides to kind of preface what some of those words mean and so forth. So why would we care about this? Why would we care about marine ice sheets and so forth? Well, I started teaching here at UCSB in 2011, and I would teach, just intro classes and so forth. And I also teach just a little seminar where I meet once a week with students about sea level changes. And when I first arrived in 2010, I would always quote that the rate of sea level rise is 2.8 millimeters per year. And that's what it was in 2010. And then in 2015, we had updated those numbers. The rate of sea level rise had actually accelerated, and it was up to 3.2 millimeters per year. And just this year, after 5 more years of satellite altimetry data and tide gauge data from across the globe, we now know that sea level is rising at a rate of 4 millimeters per year. And that is kind of following this predicted trend of an acceleration in the rate of sea level rise, such that most models project that we'll see upwards of 80 centimeters of sea level rise between now and 2100. Now, some of those models suggest that we might have even more sea level rise, and that uncertainty comes from the behavior of some of the ice streams and ice sheets over Antarctica and portions of Greenland. And one area in particular that is of concern is the ice sheets, portions of the ice sheets that are actually marine based. And why is that? Well, this kind of cartoon illustrates what I mean by a marine based ice stream or an ice sheet. So if we have a big chunk of ice, this is kind of a profile view. Let me see if I can get my cursor here. Hopefully you all can see my cursor here. This is a profile view through an ice sheet that's grounded on the bed. So the brown here is the bedrock or sediments, whatever it might be sitting on. And this dashed line here is the level of the ocean. So that's 0 in terms of sea level. And marine-based ice sheets are those ice sheets in which the grounding line, so where the ice hits the bed, is actually below sea level. And these types of ice sheets are particularly unstable because in many parts of glaciated margins, the slope of the seafloor that they have kind of advanced out onto is actually retrograding, meaning it gets deeper and deeper the further into the continent you go. And that's important for stability of the ice stream or ice sheet, because at some point, if it continues to retreat back into here, that weight is no longer able to hold the ice sheet down. It actually floats. And at the end of the last ice age, this appears to have been a mechanism by which many of the ice streams rapidly retreated. And we had a collapse of these ice streams. And that led to big increases in the rate of sea level rise during the deglaciation 20,000 years ago to about 10,000 years ago. And so before we get started, that was just a little bit of background there. There's one other thing that comes into play is these ice sheets as they're retreating are pretty dynamic. There's all sorts of interactions between the ice sheets and everything around them. And one of the important concepts is this idea of glacial-isostatic adjustment. So if we go across the globe, sea level rise isn't just like a bathtub filling up the ocean basins and then onto the shelves and the continents. The Earth itself and its gravitational field, which ultimately determines the elevation of the sea, actually deforms from the growth of the ice sheets and then the decay of the ice sheets. And as a result, we get differences in the record of sea level changes across the globe, depending on where you are located with respect to the old ice sheets. And so the best, and you've probably, heard about this before in something called post-glacial rebound, that if we go to places like Norway and Sweden, where there used to be a bunch of ice, instead of sea level rising over the last 10,000 years, sea level has actually fell because the land is coming up. And so that process where you're kind of like deforming the Earth in response to the growth and the decay of these ice sheets is sometimes referred to as glacial-isostatic adjustment, or GIA. So one kind of question that we'll try to address with the data that we collected from Scotland is the idea that potentially post-glacial rebound can stabilize marine-based ice sheets. So you can imagine in the case of this ice sheet that's just sort of retreating here, it shows a slope, but this slope is actually changing because as the ice retreats, the land actually comes up. And so there have been some suggestions that post-glacial rebound can actually stabilize and stop the retreat of these marine-based ice sheets. And so that's something that I wanted to test. If we look at the past, when ice sheets have retreated, is there evidence that post-glacial rebound may have stabilized or caused a reversal in the rate of sea level change across areas that were deglaciated at the last glacial maximum, or the last ice age, between 20 and 10,000 years ago? And so that kind of brings us to Scotland. And so Scotland and the northern British Isles used to be covered during the last glacial maximum by a big ice sheet that extended over most of northern Europe. So you can see it goes over the Barents Sea, over Fennoscandinavia, across the North Sea, and over most of the British Isles. And then as that ice sheet retreated from the end of the ice age, ultimately Scotland ended up with a little ice cap over the top of it before it disappeared. Well, on the margins of this big ice sheet, you had many zones of concentrated ice flow, like really fast glaciers. When I say fast glaciers, we're still talking at like hundreds of meters per year, not like meters per second or anything like that. They're still slow with respect to like rivers and so forth, but fast in terms of glaciers. So forgive me if I cough through this. One of the downsides of COVID, before I worked at home today, before COVID, if you got sick, you just kind of pop a couple Tylenols, power through it and go into work, but we can't do that anymore. So I'm actually grateful that I'm able to speak from home, because otherwise I'd be afraid I'd expose all you to something nasty that one of my kids brought home. So anyway, so there were many of these ice streams that flowed across the margins of the former ice sheet. And one of these was located here in what's called the Minch, which is this kind of space between northern Scotland here and some islands out here called the Outer Hebrides. And if you've ever heard or dreamed about going to the Isle of Skye, this right here is the Isle of Skye, which is at the southern edge of the Minch, which is that waterway here, and the start of this sort of big ice stream. So there has been a lot of work to kind of reconstruct the retreat history of the Minch Ice Stream across northern Scotland. So again, here is Scotland, this is Great Britain, and this is the Outer Hebrides, the Isle of Skye, and the mainland of Scotland. And what these lines are right here are different, what's called grounding zone wedges, which are basically just like giant submarine moraines that show the position of that ice stream as it retreated following the last glacial maximum. And what's interesting is if we look at the history of this, it kind of slowly retreated through here and then really took off and retreated quite rapidly on the inner part of the Minch. And this is one way that sort of illustrates that. And so this, hopefully you can see the lower one of these. These are just different climate proxies and so forth. They were trying to figure out why exactly the ice stream retreated so quickly at that time period. And so what these bars represent, this is the retreat rate in meters per year of that ice stream that flowed in the Minch from 30,000 years ago back to about 15,000 years ago. And here you can kind of see a steady retreat of about 20 meters per year until about 18,000 years ago, when it retreated at over 70 meters per year. And so what I'm going to do is basically use the record that the coast left behind to look at what sea level was doing at the time that this ice stream was retreating quite rapidly. And so the way in which we reconstructed the past sea levels is through something called isolation basins. So in areas like Scotland that at one time had a bunch of ice that flowed over the landscape, that ice sort of scoured the region and left lots of little depressions in the bedrock and lots of sort of like Rouge Montagnais and rock drumlins and so forth, a very uneven topography as it scraped clean the sort of rocks there. And northern Scotland is no exception. And this just kind of shows that topography of these little depressions and these hills and so forth. And so the idea between an isolation basin is that if this is sea level, we have a little bedrock basin here in which that basin is separated from the open ocean by some sort of bedrock sill. And as the sea level either falls beneath the elevation of that sill or rises above the elevation of that sill, this little basin goes from either marine to lacustrine or lacustrine to marine, such that we can figure out what past sea levels were doing by taking the elevation of that sill and then dating in these sediments in this basin the contact between either marine deposits and lake deposits or lake deposits and marine deposits. And those little basins in this approach, this is sometimes referred to as isolation basins. And so this is what a modern one of these little isolation basins looks like. And so here is sort of bedrock all around this little basin. There's sediments accumulating in here. and it's separated from the open ocean over here. There's the Isle of Skye. This is the Isle of Mull, by this little sill here, such that when sea level rises above the elevation of this becomes a marine basin. And when sea level drops below the elevation of this becomes a terrestrial basin. And the sediments look very different when we're looking at marine and lacustrine deposits. So then we do the fun thing where we find these old isolation basins, which are today just, and I'll show you some pictures of these that are just kind of these heath covered or these sort of marshy little swales in the topography of Western Scotland. And so what we'll do is we'll take lots of cores through here, describe the stratigraphy, try to map out this basin such that we can identify the sill, as well as the contacts between the main sedimentary units. So here in this basin, we've mapped out, this down here is the glacial deposits. The blue here is sort of the marine deposits. And these brown and striped ones, these are silts, sort of a terrestrial silt from a little freshwater lake. And then it ultimately becomes a peat bog, and that's what it's capped by. And so that's sort of the approach that we will be using to produce these new records of sea level changes. And to show you pictures of mud, these changes can be quite stark in the lithology. It doesn't take a rocket scientist to sort of map out and see these changes. So these are a couple cores from some of these isolation basins. And the pink right here, that's sort of a glacial silt. The gray here, those are marine deposits. And then the brown here on top, those are freshwater lake deposits, lacustrine deposits. And so here again, this is marine deposits, and this is lacustrine deposits. And to be a little more quantitative or a little more rigorous, we'll look at diatoms through these sediment cores to truly pick out the contact between the freshwater, sort of lacustrine deposits, and the marine silts down below. So we went out to northwest Scotland. This is the Minch, this is the Outer Hebrides, the Isle of Skye, and then far western Scotland. And there's a few small little dinky communities here that maybe have a gas station and a grocery store, but they're quite quaint and it's a nice place to work. The red stars are where we collected new sea level data from these isolation basins. And the blue are previous studies of my co-authors working up in this area of the Minch. And so the idea is then we can look at what the record of sea level rise was doing, or sea level change, as the Minch was retreating back into this basin. And so I'm going to show you some new data here from these two isolation basins near the community of Gairloch in Western Scotland. And then we took some and recalibrated some ages from some other isolation basins. So one other thing that is kind of useful about these isolation basins is, during the overall retreat, we kind of know what the overall ice sheet was doing. But there were also across Scotland some other sort of readvances of the ice during its overall retreat from the glacial maximum. So one of these you may have heard of, the Loch Lomond, which is a younger Dryas event, which is a big sort of climate event about 12.9 to 11,000 years ago. Well, a little older version of that was locally known as the Wester Ross readvance. And so these lines here show you the moraine from that so-called Wester Ross readvance. And you can see that our new isolation basins lie within those moraines, meaning that the age of this advance had to be older than the oldest ages within our marine basins, our isolation basins, because you couldn't have had ice there when you had marine waters. And so this is the first of our isolation basins. Forgive my Gaelic, so I'm sure I'm slaughtering these names, but this is Loch Bonna Claise. And so here is the basin. Today it's filled mostly as a freshwater lake. And the outlet, which provides the sill, is right down here. And so we took our cores just on the other side of this little hill within this overall basin. And so this is just kind of what the landscapes look like. This is heath, which is basically just this peat. It's kind of funny when you're in these little lowlands, you can kind of jump and bounce on the ground. And since it's all just peat, it's kind of like a trampoline. It's kind of eerie as you're walking across it because the land kind of moves beneath you. And so we took several cores in this little basin. And here we were then able to map out the stratigraphy in the subsurface. And here we can see the base is the pink. That's the glacial deposits. The blue here is the marine deposits. Excuse me. And then the browns and grays here are those lacustrine deposits. And then it's all capped by 1 to 2 meters of peat on top of it. And so we get this classic sequence of pink silt, blue marine, brown lacustrine, and then the peat on top of it. And we got 7 radiocarbon ages from sort of the middle of the basin, and they're all in sort of stratigraphic order, and they date back to about 15.9 thousand years ago. And now, forgive me for this little detour, but when we were there, Durham had a really nice little magnetic susceptibility, and I think I saw Zach on there, and Zach did some magnetic susceptibility when he was a student at UCSB. And it's a really nice one where you just kind of set the core in there, and it's a line scan magnetic susceptibility. And oops, I jumped ahead of myself. We'll come back to the magnetic susceptibility here in just a second. This is the magnetic susceptibility. Just to show you, we're not just looking at the colors, but we actually did the diatoms to identify the contact between the marine part of the core, so here with the blue colors, and the lacustrine part of the core, which is here in the green colors. And so that lines up to be right where we see the contact between the blue silts and sort of the gray and brown, or excuse me, the gray blue silts and sort of the brown organic rich silts. So next I'm going to look at what's kind of something very interesting about the magnetic susceptibility here. What I show here, this is the magnetic susceptibility thrown on its side. So this is from 200 centimeters depth down to about 5.5 meters depth. And I've thrown many proxies for climate out here. These are from ice cores from Greenland, the blue ones here. This one is the abundance of a certain type of insect larvae in one of these bogs that they can then translate to air temperatures in July for Scotland. And then this is a marine core from just offshore. And what I thought was neat is that the magnetic susceptibility, which tracks sort of climate almost 1 for 1, in that we see high magnetic susceptibility, which basically equates to low productivity, not a lot of organic material, when we had cooler periods like the Younger Dryas, and before a couple warm periods known as the Allerad Bowling and the Allerad. And that we can see that in the magnetic susceptibility. And so we have a really nice record sort of climate from this isolation basin. And what's neat is you can also see that within the core itself. And so here's that pink silt, the marine silt, the lacustrine, and then you can see areas of more organic material. Those turn out to be periods of warmth, known as the Bowling and the Allerad, and then the Younger Dryas and the Older Dryas. Okay, so forgive me for that little tangent, but it'll play important here in just a minute. So that was the first isolation basin, Loch Bonna Claise. And this is Loch Butyl, which is another set. There's a higher basin here, which we cored and has no marine. And then a lower basin here, which is the one we focus most of our time. And there in the distance, that's the other isolation basin that I showed you just a minute ago. And so we did the same thing. We took cores, mapped out the basin. We had pink, marine, brown silt. Unfortunately, the ages weren't as clear cut as they were within the others. They were sort of a mixture of ages all within the same area. And I think we know why that happened. But anyway, we know the sill elevation. We know, at least we think we know the elevation of that contact. So then we can start to put these data together to come up with a sea level record for Western Scotland. And so there was a little nuance here, and that had to do with the higher basin being younger than the lower basin, which is not what we expect, but the magnetic susceptibility tells us that we're actually missing a section of that core, which then would explain the reworked ages. And we think that is because of the setting and the sea ice that was there. It turns out this basin would have only been 2 meters deep. And in similar settings today, during the winter, those basins will freeze all the way to the seafloor. And you can imagine that ice would probably rework these sediments. The other basin was 4 meters deep, and it's less likely that it would have frozen all the way through on that 4 meter deep basin. Okay, so then one more series of isolation basins. This is Glacial-isostatic. I know I'm ruining my Gaelic here, but there are 3 isolation basins. This one never saw marine deposits. This is the one I'm going to show you data from right there. So we took cores through here, and at first we thought we found something quite exciting, in that there's always been this idea that potentially in Northwest Scotland, you might find periods where you go from marine to lacustrine, back to marine, back to lacustrine, and then the normal sequence. And when we first took our cores, we found something that looked like that. And this kind of shows it in this core. This is one of those cores. It goes the gray, which is marine, into lacustrine, back to marine, and then back to lacustrine. And the reason why we were excited about this when we first found this is that there was at about this time period, as the ice sheets were retreating, there was this time period known as meltwater pulse 1A, when sea level rose 20 meters in 200 years. And sometimes that's hard to put into perspective. Sea level rising 20 meters in 200 years. And so I tell students that means in the time that it takes you to finish your degree, sea level would have risen a foot if you were going to school during meltwater pulse 1A, 14,500 years ago. Okay, why is that important for sort of a sea level reversal here in Scotland? Well, there have been many predictions suggesting that Scotland would have a kind of sea levels falling, rises during meltwater pulse 1A, and then continues to fall if the source of that meltwater, that 20 meters of sea level rise, came from Antarctica. And so we thought, hey, here's proof that, meltwater pulse 1A came from Antarctica. Well, unfortunately, when we did the radiocarbon ages on this core, they're all out of order, suggesting that this is not a true sedimentary sequence, but probably some sort of slumping that occurred within this. But nevertheless, this does tell us minimum estimates of deglaciation and relative sea level change. So forgive that other tangent there. Okay, so now we've collected some new sea level data. We have some new ages that kind of constrain the retreat of the ice sheet. Now we can take our new ages, and then we can take all the existing ages and sort of refine the model of the retreat history of that Minch ice stream. And so we do that in a statistical program known as OxCal, which basically looks at the error bars on your ages, takes into account that, there had to be a sequence of these events that can then narrow down the timing of your events. And so we did that, refined the timing of the Minch ice stream. And then now that we have a good model for the timing of the retreat, we now want to go back and examine what the rate of sea level rise was as the Minch ice stream retreated. Now, we collected several locations of sea level change from looking at our isolation basins, but we don't have a full view of sea level rise at every location throughout the retreat, of that ice stream. And so what we turn to is models of that GIA, that glacial isostatic adjustment. And there are still some uncertainties about which models best replicate the sea level history for this part of Scotland. And so what these GIA models are is they basically take, a spherical Earth, then they load the Earth with different models of ice sheets, and then knowing what we know about the sort of thickness of the lithosphere and the rheology of the mantle, they can actually predict what the Earth does to come up with sea level changes at any location on the globe, not just those places where we actually have data. And so here, what we do is we take our new sea level data and then use it to test these models to see which one best predicts what sea level is doing there for this part of Scotland. And so this is relative sea level change. And, here is 0. This is higher sea levels than present. Remember, this is an area where the land is coming up, so it makes it look like sea level is falling for part of the time period. And then this is back in time from the present back to 20,000 years ago. And the little blue boxes here, that shows the time period when the area was covered by ice. And then everything to the left of that is where we should be able to get sea level data because there wasn't any ice there. And so we would be preserving things like isolation basins and so forth. So hopefully you're following me and I haven't lost you yet or bored you to death. Okay, so it turns out of our different sea level models, this one particularly works best. And that's not surprising because it tends to be the best predictor of sea levels for Scotland. Okay, so now we turn to trying to understand what the rate of sea level rise was at the front of the Minch ice stream. Now, remember, when we're reconstructing sea levels, we're looking at the record of sea level at one particular place on the landscape. But the thing about the Minch is the front of that ice stream is not staying in the same location. It's actually retreating back into the inner reaches, back towards the Isle of Skye, such that the sea level record at any one location doesn't tell you the sea level record experienced by the front of that ice stream, and hence what's going to be driving its retreat. And so I'm going to be showing you some different plots than what we typically think of when looking at sea level change. And so here is just, sea level on the y-axis, time on the x-axis. And if we want to know what the record of sea level change experienced by the ice stream is, we kind of have to put that together from many different individual sea level curves that exist through the retreat of that ice stream. And so what this kind of shows is how we did that. So C right here is the record of sea level change. Let's start with A, sorry. A here, this blue line, is what sea level's doing at this location out on the shelf. the blue line A here. B, that's the sea level curve experienced at this location in Northwest Scotland. And then C is the record of sea level change experienced here at the Isle of Skye, such that if we want to know what the rate of sea level change experienced by the Minch is, we basically connect the dots for the time periods it crosses each one of those locations. And so that's what these next charts are going to show. And so this is relative sea level on the y-axis. This is time in thousands of years before present on the x-axis. These colored lines here are the sea level experienced at different positions along the retreat of the Minch ice stream, such that if we connect the dots of its location, we actually can see what the sea level change experienced by the front of that ice stream as it's retreating. And so one thing I want you to notice in the Kuchar model, but every other model that we use, is all of them show the same different thing. And that is sea level is either rising slowly or potentially falling up until about 17,000 years ago, where it sees a dramatic increase in the rate of sea level rise, or it's actually going from sea level fall to sea level rise. Well, this period right here is also the time period when that ice stream starts to really collapse. And we think that the reason that it really started to retreat is that that is the point in which it went from experiencing falling sea level to rising sea level. Hopefully that makes sense. We can plot that a different way, and that's what this sort of plot shows. And so each one of these points tells you the rate of sea level change experienced at the same time that that ice stream is retreating at this rate. And so basically when the numbers are way up here, that ice stream, that's when the ice stream is retreating really fast. And when the numbers are down here, the ice stream is retreating very slow. And so what we can see is when that ice stream is experiencing sea level fall, it's not retreating very fast. But as soon as it starts to experience a period of sea level rise, then it starts to retreat extremely fast. So what does all this mean? Okay. Now, although foredeepening likely played a role in the retreat of the Minch ice stream, it also probably sea level started to rise only when the ice stream started to retreat quite rapidly. And so sea level probably contributed to the retreat of that ice stream. And so one question we also might ask is, as the ice stream retreated, it did not experience an RSL fall as predicted by some of those models. So we might ask why? Why did it not retreat fast like this model about post-glacial rebound causing sea level to actually fall, but it retreated? Well, we think that there were two reasons for a sea level rise instead of a fall during the retreat of the Minch ice stream. One thing is the models that suggest that they use a 2D model for the ice sheet. And that means that it's assuming that that ice sheet is like a sphere or a circle, and that it's radially symmetric, and the whole ice sheet is shrinking in at the same time. Well, in many parts of glaciers, like the Minch Ice stream that I just showed, and then in portions of Antarctica, the retreat is actually focused along little indentations in the ice stream. And the GIA, the isostatic adjustment of the Earth, is governed not by just the front of that ice stream, but the overall ice sheet. And in the case of the Minch Ice stream, although it was retreating down that narrow little trough, there was still ice remaining to the east and the west that did not retreat and hence did not cause the land to rebound. And then a second reason is these models are calibrated to a really weak Earth, like what we find beneath West Antarctica. And under Scotland is old crust. If the rocks that we were looking out there were of a billion or half a billion year old sandstone, right? Those are really old rocks. That is a pretty mature margin. And so the lithosphere is pretty thick, and the mantle has a pretty high viscosity, and so it doesn't retreat as rapidly as what these models for West Antarctica suggested. So what does all that mean? Is that in areas like East Antarctica and Northeast Greenland, where we have a really thick lithosphere, and in areas where most of the retreat is going to be confined to these narrow troughs, that post-glacial rebound will not stabilize these marine-based ice sheets. And then we can wave our arms about, we kind of also refined the age of the Western Ross Marine Advance. We found it to be about 1,000 years older than what we thought it initially thought it was. So just some thanks to many students that helped collect some of these cores, and to John Southern and Dylan Osliger, who helped with some of the radiocarbon dating. And then I had some discussions with Devin and Lorraine at UCSB to help me with the magnetic susceptibility correlations. So thank you.
All right, thanks, Alex. I finally figured out how to unmute on Zoom. I'm usually